Hello and welcome to Bedside Physics. Before we begin, take a moment to like the video, subscribe to the channel, and let me know where you're watching or listening from tonight. Whether you're curled up at home, traveling somewhere far away, or simply drifting between waking and sleep, it's quietly fascinating to think that wherever you are, the same invisible fields fill the space around you and within you, just as they do everywhere else in the universe. Now, settle in. Tonight we're going to gently explore a question that sounds simple, but leads us somewhere surprisingly deep. What is everything made of? At first glance, the answer feels obvious. We're made of atoms. Atoms are made of particles, tiny, solid, fundamental pieces of reality. But as we look closer, that picture begins to soften. The solid world you feel, the weight of your body, the surface beneath you, the quiet presence of objects around you, turns out not to be made of solid things at all. Instead, modern physics suggests something far more subtle. Beneath everything we see and everything we are, there are no truly separate objects. There are only fields. Invisible, continuous fields that stretch across all of space, unbroken, ever-present, quietly active, and what we call particles, the building blocks of matter, are not little beads or points in space. They are tiny vibrations, gentle ripples, localized excitations in these deeper underlying fields. A single electron is not a thing in the usual sense. It is a small, persistent pattern, moving through an invisible ocean that fills the entire universe. And perhaps even more surprisingly, that ocean isn't just out there in distant space. It is here, right now, in the air around you, in the space between your thoughts, in the very fabric of what feels like emptiness. Even what we call nothing is quietly full of motion, full of possibility, full of fields that never truly rest. So tonight, we're going to slowly unfold this picture together. We'll begin with the familiar idea of atoms and particles, and gently move beyond it. We'll explore how physics shifted from thinking in terms of solid objects to understanding reality as something more fluid, more interconnected. We'll see how quantum fields emerged as one of the most successful and most quietly profound ideas in all of science. And along the way, we will touch on deeper questions about whether reality is made of things at all, or whether it's made of relationships, patterns, and processes. Questions about whether empty space is truly empty, or whether it's the most active and fundamental layer of the universe. And perhaps, as we move slowly through these ideas, you may begin to feel something unexpected. Not confusion, but a kind of calm curiosity. A sense that the universe, in all its complexity, is also quietly simple, not built from countless separate pieces, but from a small number of underlying patterns repeating in endlessly different ways. So, as you listen, there's nothing you need to hold on to too tightly. Let the ideas drift past like gentle waves, and if you begin to lose track, that's perfectly fine. Because in a way, what we're exploring tonight is not just a theory of physics, it's a different way of seeing, a way of noticing that beneath everything familiar, there is a deeper, quieter structure, always there, always present, softly building the universe, moment by moment. When we look around, everything seems reassuringly solid. The surface beneath you feels firm. The objects in the room appear stable as well defined. Even your own body seems like a clearly bounded thing, made of substance, occupying space in a straightforward way. From a very early age, this is how we learn to understand the world. We learn that things are made of smaller things, and those smaller things are made of even smaller ones. Tables are made of wood. Wood is made of molecules. Molecules are made of atoms. And atoms, we are told, are made of particles, tiny, indivisible pieces of reality, little building blocks that sit in space like grains of sand. It is a comforting picture, simple, tidy, and easy to imagine. But as physics has gradually uncovered deeper layers of nature, this picture has begun to shift. Not suddenly and not dramatically, but slowly, quietly, and with increasing clarity. The deeper we look, the less the universe seems to be made of solid, independent things, and instead it begins to look more like a collection of ongoing activities, patterns, movements, processes unfolding over time. To get a sense of this, it helps to pause and reconsider something very familiar. Take a moment to imagine an ocean. From a distance, you might notice waves moving across the surface. Each wave appears to have a shape, a position, yet even a kind of identity. You might point to one and say, "There is a wave." But if you look more closely, the wave is not a thing in the same way a rock is a thing. It is not made of a fixed set of water molecules travelling together across the ocean. Instead, it is a pattern, a coordinated motion. The water itself mostly stays in place, gently rising and falling. What moves is the pattern of that motion. The wave is something that happens, not something that simply is. And in a quietly profound way, modern physics suggests that much of reality may be like this. What we call objects, what we call particles, may not be fundamental things at all. They may be stable patterns in something deeper. This idea has echoes outside of physics as well. In the early 20th century, thus the philosopher Alfred North Whitehead proposed what he called process philosophy. Rather than viewing reality as composed of static objects, Whitehead suggested that the fundamental elements of the universe are events, moments of becoming, processes unfolding in time. In his view, what we perceive as stable things are really just persistent patterns within a flow of activity. At the time, this was a philosophical proposal, not a physical theory. But interestingly, as physics has developed, it has moved in a direction that feels strikingly similar. Instead of focusing on solid, indivisible particles, modern theories increasingly describe the world in terms of fields, interactions, and dynamic structures. Even the idea of a particle, something that seems so basic, begins to soften under closer inspection. In quantum physics, particles do not behave like tiny billiard balls. They do not have sharply defined positions and trajectories in the classical sense. They do not move through space in smooth, predictable paths. Instead, they exhibit behaviors that are better described in terms of probabilities, interactions, and underlying mathematical structures. And as we move further into the framework of quantum field theory, the shift becomes even more pronounced. Particles are no longer treated as fundamental objects at all. They are understood as excitations, small, localized disturbances in underlying fields that extend throughout all of space. In other words, they are closer to waves than to things, closer to events than to objects. And this brings us back to the idea of patterns. If a particle is a localized vibration in a field, then what we're observing is not a tiny piece of matter travelling through empty space. We're observing a pattern of activity in something that is already there, something continuous, something ever-present. This perspective invites a different way of thinking about reality. Instead of imagining the universe as a collection of separate objects sitting in space, we begin to see it as a network of interacting processes, a kind of continuous unfolding. And this shift becomes even more intriguing when we consider how these processes relate to one another. Carlo Rovelli, a theoretical physicist known for his work on quantum gravity, has proposed an interpretation of quantum mechanics called relational quantum mechanics. In this view, the properties of physical systems are not absolute. They do not exist independently of observation or interaction. Instead, they are defined through relationships. A particle does not simply have a position or a velocity in an absolute sense. These properties arise in relation to other systems. What something is depends on how it interacts. This idea can feel a little unfamiliar at first. We're used to thinking of objects as having intrinsic properties. A chair is a chair, regardless of whether anyone is looking at it. But at the quantum level, things are not quite so straightforward. Properties emerge through interaction, through connection, through participation in a wider network of processes. And when we combine this relational perspective with the idea of fields and excitations, a new picture begins to take shape. Reality is not built from isolated pieces. It is woven from interactions, from patterns that arise, persist for a time, and then dissolve back into the underlying structure. Even what we perceive as stability, the apparent permanence of objects, can be understood as a kind of dynamic balance, a stable pattern that maintains its form through ongoing activity. Your body, for example, is not made of the same atoms it was made of several years ago. Atoms are constantly being exchanged with the environment. Molecules are broken down and rebuilt. Energy flows in and out. And yet, the pattern remains. You remain. In a sense, you're not a fixed object. You are a process, a beautifully organized, continuously evolving pattern of interactions. And the same may be true in different ways for everything else. The chair in the room, the air around you, the distant stars. Then each is a stable arrangement of deeper activity. Each is a pattern that persists for a time within a wider, more fundamental structure. This way of seeing the universe can feel both unfamiliar and strangely calming. Unfamiliar, because it gently dissolves the idea of solid, independent things, but calming because it replaces that idea with something more fluid, more interconnected, a sense that everything is part of a continuous whole, not separate pieces, but interwoven processes. And as we continue, this perspective will become more concrete. We will begin to explore what these underlying fields are, how they behave, and how they give rise to everything we observe. But for now, it is enough to hold on to this simple shift. The idea that beneath the surface of everyday experience, beneath the apparent solidity of the world, reality may not be made of things at all, but of patterns, of relationships, of processes quietly unfolding everywhere, all the time. Long before modern physics began to describe fields and vibrations, there was a much simpler idea. The idea that everything is made of tiny, indivisible pieces. If you go back more than 2,000 years to ancient Greece, you find one of the earliest versions of this thought in the work of Democritus. He proposed that if you kept dividing matter again and again, cutting it into smaller and smaller pieces, you would eventually reach something that could not be divided any further. He called these ultimate pieces atomos, meaning uncuttable. It was a remarkably intuitive idea, simple, elegant, and in some ways very close to how we still talk about matter today. But at the time, it was purely philosophical. There were no experiments, no measurements, no microscopes to confirm or challenge the idea. It was a way of thinking about the world, rather than a scientific theory. For many centuries, this idea remained in the background, competing with other views. Aristotle, for example, argued that matter was continuous rather than made of discrete pieces. In his view, substances could be divided endlessly without ever reaching a smallest unit, and for a long time this continuous view of matter was the more influential one. It was not until the early 19th century that the atomic idea returned in a scientific form. John Dalton, an English chemist working in the early 1800s, proposed a modern atomic theory based on careful measurements of chemical reactions. He observed that substances combine in fixed ratios by mass. For example, water is always formed from hydrogen and oxygen in a consistent proportion. From this, Dalton concluded that matter must be made of discrete units, atoms, that combine in simple numerical ratios. It was a powerful step forward. For the first time, atoms were not just philosophical ideas, they were part of a testable scientific framework. But Dalton's atoms were still imagined as solid, featureless spheres, tiny, indivisible balls of matter. And as experiments became more precise, this picture began to break down. In the late 19th century, J.J. Thomson conducted experiments with cathode rays, streams of charged particles moving through vacuum tubes. By studying how these rays responded to electric and magnetic fields, Thomson discovered something unexpected. He had found a component of the atom, a much smaller particle, later called the electron. This meant that atoms were not indivisible after all. They had internal structure. Thomson proposed a model sometimes called the plum pudding model, where negatively charged electrons were embedded within a positively charged background. It is not the most appetizing analogy, but it was a sincere attempt to make sense of new evidence. Soon after, Ernest Rutherford performed his famous gold foil experiment. In this experiment, alpha particles were directed at a thin sheet of gold. Most passed straight through, but a small number were deflected at large angles with a few even bouncing back. This was deeply surprising. It suggested that most of the atom is empty space, with a dense, positively charged nucleus at its centre. Rutherford's model replaced Thomson's, and once again the picture of the atom changed. Now it was mostly empty, with a tiny nucleus and electrons somehow arranged around it. But this raised new questions. If electrons were orbiting the nucleus like planets around the Sun, why did they not spiral inward and collapse? According to classical physics, accelerating charges should emit radiation and lose energy, yet atoms are stable. Niels Bohr introduced a new idea in the early 1900s. He proposed that electrons occupy specific, quantized energy levels, and that they can only move between these levels in discrete steps. This helped explain the stability of atoms and the spectral lines observed in experiments. It was a partial solution, but not a complete one, because beneath all these models, something deeper was still unresolved. Even as the structure of the atom became more detailed, the underlying nature of matter remained unclear. And alongside these developments, other thinkers were quietly reshaping how we understand physical systems more broadly. Ludwig Boltzmann, working in the late 1800s, developed statistical mechanics. Rather than focusing on individual particles, Boltzmann described systems in terms of probabilities and distributions. He showed that properties like temperature and pressure emerge from the collective behavior of vast numbers of microscopic components. In a gas, for example, there are on the order of 10 to the power of 23 molecules in a single mole. yet tracking each one individually would be impossible. Instead, Boltzmann's approach treats the system statistically, describing patterns rather than precise details. This was an early step toward thinking in terms of collective behavior, something that will become increasingly important later. Henri Poincaré, another influential figure, explored the mathematical structure of physical systems. He studied dynamical systems and the sensitivity of complex systems to initial conditions. In doing so, he revealed that even simple systems can exhibit unpredictable behavior over time. This hinted at a deeper layer of complexity beneath classical mechanics. What these contributions have in common is a gradual shift in perspective, away from the idea of perfectly predictable, indivisible objects, and toward a view of systems as dynamic, probabilistic, and interconnected. And yet at this stage the dominant picture of matter was still particle-based. Atoms were made of smaller particles. Those particles had positions, masses, and charges. They existed in space, moving and interacting. But as the 20th century unfolded, even this refined particle picture would begin to dissolve. Experiments in quantum mechanics revealed that particles do not behave like classical objects. They do not have well-defined positions and velocities at the same time. They exhibit wave-like behavior, interference patterns, and probabilistic distributions. The very concept of a particle became more subtle, less like a tiny object, and more like something that resists simple categorization. Here, what began as a straightforward idea, indivisible building blocks of matter, had evolved into something far more complex. Atoms were divisible. Their components behaved in unfamiliar ways, and the deeper we looked, the less solid everything seemed. It is almost as if each layer we uncover brings us closer, not to a final simple object, but to a deeper question. What are these particles really? Are they truly fundamental pieces of reality? Or are they, like waves on the ocean, expressions of something more underlying, a pattern rather than a thing? As we move forward, this question becomes increasingly important, because the journey from atoms to particles is not the end of the story. It is the beginning of a much more subtle and intriguing way of understanding the universe. As the picture of the atom became more detailed, something unexpected began to happen. The closer physicists looked, the less the world behaved in ways that matched everyday experience. At first, the changes were subtle, small inconsistencies, tiny cracks in the classical description of nature. But over time, those cracks widened into something much deeper. A realization that the familiar rules of motion, position, and cause and effect were not the full story. One of the earliest signs of this came from a problem involving something as ordinary as heat and light. In the late 1800s, physicists were trying to understand how objects emit radiation when they are heated. This is known as blackbody radiation. If you heat a piece of metal, it glows red, then orange, then white as the temperature increases. Classical physics attempted to describe this process, but it led to a strange and troubling prediction. At high frequencies, the equation suggested that the energy emitted should become infinitely large. This was called the ultraviolet catastrophe. Clearly, this did not match reality. In the year 1900, Max Planck proposed a solution that was both simple and radical. He suggested that energy is not emitted continuously, but in discrete packets, small, indivisible units that he called quanta. This idea can be expressed in a simple relationship. Energy equals Planck's constant multiplied by frequency. This means that the energy of radiation is tied to its frequency in fixed steps. At the time, Planck saw this as a mathematical trick, a way to make the equations fit the data. But it turned out to be something much more fundamental. A few years later, in 1905, Albert Einstein took this idea further while studying the photoelectric effect. In this experiment, light shining on a metal surface can eject electrons. Classical wave theory predicted that increasing the intensity of light should increase the energy of the emitted electrons. But experiment showed something different. It was not the intensity that mattered most. It was the frequency. Below a certain threshold frequency, no electrons were emitted at all, no matter how bright the light was. Einstein explained this by proposing that light itself is quantized. It comes in discrete packets, later called photons. Each photon carries a specific amount of energy determined by its frequency. If the photon has enough energy, it can eject an electron. If not, nothing happens. This was a profound shift. Light, and which had long been understood as a wave, was now behaving like a particle, and soon the reverse would also become true. Particles would begin to behave like waves. This dual behavior is known as wave-particle duality. It is one of the central features of quantum mechanics. To see how unusual this is, consider the double-slit experiment. If you send particles, such as electrons, toward a barrier with two narrow openings, you might expect them to pass through one slit or the other, forming two clusters on a screen behind. But when the experiment is performed carefully, something remarkable happens. Even when electrons are sent one at a time, the pattern that builds up on the screen shows interference. A series of bright and dark bands characteristic of waves interacting. Here it is as if each electron is passing through both slits at once, interfering with itself, and then arriving at a single point on the screen. This is not how classical objects behave, and it becomes even more puzzling when you try to observe which slit the electron goes through. The act of measurement changes the outcome. The interference pattern disappears, and the electrons behave more like classical particles. This strange behavior is not a flaw in the experiment. It has been confirmed repeatedly, with extraordinary precision. It reflects something fundamental about how nature operates at small scales. Werner Heisenberg captured part of this in what is known as the uncertainty principle. It states that there is a fundamental limit to how precisely certain pairs of properties can be known at the same time. Most famously, position and momentum. The more precisely you know where a particle is, the less precisely you can know how fast it is moving. And this is not due to imperfect instruments. It is built into the structure of reality itself. The principle can be expressed as a relationship between uncertainties. The uncertainty in position multiplied by the uncertainty in momentum is greater than or equal to a small constant related to Planck's constant. This means that at very small scales, the idea of a particle having a definite position and velocity at all times simply does not apply. Niels Bohr approached this from a slightly different angle with his principle of complementarity. He suggested that quantum systems can exhibit different, mutually exclusive properties depending on how they are observed. In one experimental setup, light behaves like a wave. In another, it behaves like a particle. Both descriptions are necessary, but they cannot be applied simultaneously in a straightforward way. This is not just a limitation of our knowledge, it reflects a deeper feature of quantum systems. They do not fit neatly into classical categories. Instead, they require a new kind of description. And despite the extraordinary success of quantum mechanics in predicting experimental results, its interpretation remains open to discussion. John Archibald Wheeler, a theoretical physicist, proposed a striking idea known as it from bit. He suggested that physical reality may ultimately arise from information, that what we call particles, fields, and forces might be secondary, emerging from more fundamental acts of measurement or interaction. In this view, the universe is not built from objects, but from informational relationships, a kind of participatory process where observation plays an essential role. Another modern perspective comes from Cubism, or quantum Bayesianism, developed by Christopher Fuchs and collaborators. In Cubism, the wave function is not a physical object in the world. Instead, it represents an observer's knowledge or expectations about a system. Quantum mechanics, in this interpretation, is a tool for managing uncertainty and updating beliefs based on experience. It is less a description of reality itself, and more a guide for navigating it. These interpretations differ in important ways, but they share a common theme. They suggest that quantum mechanics may not be telling us a simple, objective story about what exists independently of observation. Instead, it may be revealing something more subtle about the relationship between observer and system, between knowledge and reality. And yet, despite these conceptual challenges, quantum mechanics works. It works with extraordinary precision. It allows us to predict the behavior of atoms, design semiconductors, build lasers, and understand the structure of matter. Its equations have been tested to many decimal places and found to be accurate. So we find ourselves in an interesting position. We have a theory that is incredibly successful, and yet in some sense not fully understood. A framework that describes the world with remarkable accuracy, but resists simple interpretation. It tells us how things behave, but not always what they are. And perhaps most importantly, it gently loosens our grip on classical intuition. The idea that particles are tiny objects moving along definite paths, the idea that properties exist independently of observation, the idea that the world can be described in purely deterministic terms, all of these begin to soften. In their place, we're left with something more flexible, a picture of reality that includes probability, interaction, and context. A picture where the act of measurement is not just passive observation, but an active part of the process. And as we continue to explore this landscape, one idea will become increasingly important. If particles do not behave like simple objects, if their properties depend on deeper structures and interactions, then perhaps they are not fundamental after all. Perhaps they are, like waves on the surface of an ocean, expressions of something deeper, and something more continuous, something that fills all of space. And it is this idea that will guide us toward the concept of quantum fields. To begin understanding quantum fields, it helps to first become comfortable with a simpler idea, the idea of a field itself. It is a word that appears often in physics, but it can feel a little abstract at first. So it is worth slowing down and building a clear, intuitive picture. Imagine you are standing outside on a cool evening. Around you, the temperature is not the same everywhere. Some areas might feel slightly warmer, others slightly cooler. If you could assign a number to the temperature at every point in space, every location around you, you would have what physicists call a temperature field. A field, in its simplest form, is just a way of assigning a value to every point in space. That value could be a temperature, it could be a pressure, it could be something more abstract like a direction or a force. but the key idea is continuity. A field exists everywhere, not just in one place. It fills space. Another familiar example is the gravitational field of the Earth. Every object with mass creates a gravitational field around it. If you hold a small object in your hand and let it go, it accelerates downward. This happens because the Earth's gravitational field is acting on it. Near the surface of the Earth, this field has a strength that causes objects to accelerate at about 9.8 meters per second squared. And importantly, this field exists whether or not anything is there to experience it. Even in empty space, the field is present. And this idea began to take a more precise form in the 19th century, largely through the work of Michael Faraday. Faraday was not a mathematician in the traditional sense. He was an experimental physicist with a strong intuition for how nature behaves. He introduced the concept of field lines, a way of visualizing how forces extend through space. If you sprinkle iron filings around a magnet, they arrange themselves in patterns that reveal the magnetic field. These patterns are not just visual tricks. They represent something real, a structure in space that influences how objects behave. Before Faraday, forces like magnetism and electricity were often thought of as acting at a distance. Two objects would somehow influence each other instantly, even if separated by empty space. Faraday's insight was different. He proposed that the space between objects is not empty in a passive sense. It is filled with fields that carry the influence from one place to another. This was a significant shift. Forces were no longer mysterious actions at a distance. They became local interactions mediated by fields that exist throughout space. James Clerk Maxwell later translated Faraday's ideas into a precise mathematical framework. Maxwell developed a set of equations that describe how electric and magnetic fields behave and interact. These equations showed that changing electric fields can produce magnetic fields, and changing magnetic fields can produce electric fields. Together, they form what we now call the electromagnetic field. One of the most remarkable predictions of Maxwell's equations is that electromagnetic disturbances can travel through space as waves. These waves move at a specific speed, and when that speed was calculated, it matched the known speed of light. This led to a profound realization. Light itself is the electromagnetic wave, not a stream of particles as once thought, but a vibration in a field that fills all of space. This was one of the first clear indications that fields are not just useful mathematical tools. They are physically real. They can carry energy. They can propagate through space. They can interact with matter. And they can exist even in regions where there are no particles at all. This begins to hint at a deeper possibility. What if fields are not just descriptions of how forces act? What if they are the fundamental ingredients of reality? This idea was explored in different ways by various thinkers. One particularly interesting figure is William Clifford, a 19th century mathematician and philosopher. Clifford suggested that matter might not be a separate substance at all. Instead, he proposed that what we perceive as matter could be a manifestation of the geometry of space itself. In his view, small regions of space could be curved or distorted, and these distortions might appear as particles. This was a speculative idea, but it anticipated later developments in physics. Albert Einstein's general theory of relativity, for example, describes gravity as the curvature of space-time. Mass and energy influence the geometry of space-time, and that geometry determines how objects move. While this is not the same as Clifford's proposal, it shares a similar spirit. the idea that what we perceive as physical phenomena may arise from deeper structures. Returning to fields, we can now begin to see how they differ from particles in a fundamental way. A particle is typically thought of as something localized. It exists at a particular position in space. It has a defined location, even if that location is not always precisely known. A field, on the other hand, is spread out. It exists at every point in space simultaneously. It is not confined to a single location. This difference has important consequences. If fields are fundamental, then particles might not be the basic building blocks of reality. Instead, particles could be seen as localized features within fields, much like a ripple on the surface of water. Now, the ripple is not separate from the water. It is a pattern within it. And just as a wave can move across the ocean without the water itself traveling long distances, a disturbance in a field can move through space, carrying energy and momentum, but not necessarily involving the movement of a fixed substance. This way of thinking begins to unify several ideas we've encountered: the wave-like behavior seen in quantum experiments, the continuous nature of fields in classical physics, the idea that properties emerge through interaction rather than existing independently. All of these point toward a picture of reality that is less about isolated objects and more about continuous structures and dynamic patterns. At this stage, we are still dealing with classical fields that vary smoothly and continuously, as described by equations like those of Maxwell. But as we bring quantum mechanics into the picture, something new emerges. Fields themselves begin to exhibit quantum behavior. They become subject to uncertainty, fluctuation, and discrete excitations. And this leads to one of the most important developments in modern physics: the idea that every type of particle is associated with its own field, a field that exists everywhere in space, and that what we call a particle is simply a small quantized excitation of that field, a tiny vibration in something that is always present. This is the beginning of quantum field theory, and it offers a way to bring together the insights of quantum mechanics and the concept of fields into a single coherent framework. A framework in which the universe is not built from separate pieces, but from fields that fill all of space, quietly giving rise to everything we observe. By this point, two powerful ideas have emerged, each remarkably successful on its own: quantum mechanics, which describes the strange and probabilistic behavior of particles at very small scales, and relativity, developed by Albert Einstein, which describes how space and time behave, especially at very high speeds and in strong gravitational fields. Each of these theories works with extraordinary precision in its own domain. Quantum mechanics explains the structure of atoms, the behavior of electrons, and the properties of light. Relativity explains the motion of planets, the bending of light near massive objects, and the expansion of the universe. But for a long time, these two frameworks did not sit comfortably together. Quantum mechanics was built on probabilities and uncertainties. Relativity was built on smooth, continuous space-time and strict relationships between energy, mass, and motion. Bringing them together required a new way of thinking, and this is where quantum field theory begins to take shape. One of the key figures in this development was Paul Dirac. In the late 1920s, Dirac was searching for a way to describe electrons that was consistent with both quantum mechanics and special relativity. He developed what is now known as the Dirac equation, a mathematical framework that successfully combined these two theories. But what made this equation especially remarkable was what it predicted. It suggested the existence of particles with the same mass as the electron, but with opposite charge. At the time, this seemed purely theoretical. But a few years later, in 1932, the positron was discovered experimentally by Carl Anderson. It was the first confirmed example of antimatter. This was a powerful demonstration that mathematical structures in quantum field theory could reveal entirely new aspects of reality. Not just describe what we already observe, but predict what we have yet to find. As the theory developed further, a deeper picture began to emerge. Instead of treating particles as the fundamental entities, quantum field theory treats fields as primary. Each type of particle corresponds to a specific field that exists throughout all of space. There is an electron field, a quark field, a photon field. These fields are not confined to particular regions. They are everywhere, even in what we would normally call empty space. And what we observe as a particle is simply a small excitation of one of these fields, a localized vibration. If you could, in some sense, remove all excitations from a field, calm it completely, the field itself would still remain. It does not disappear. It is part of the underlying structure of reality. This leads to a profound shift in perspective. Instead of imagining the universe as a collection of particles moving through empty space, we begin to see it as a collection of fields, continuous, overlapping, and always present. Particles are no longer the building blocks, they are the visible features, the ripples, that arise within these fields. To make this more concrete, consider again the analogy of a musical instrument. Imagine a violin string. The string itself is always there, even when it is perfectly still. When it vibrates, it produces sound. Different modes of vibration correspond to different notes. In a similar way, a quantum field can vibrate in discrete ways. Each allowed vibration corresponds to a particle with specific properties, such as mass and charge. The field is the underlying structure, the particle is the excitation. This idea has been developed and refined over many decades. Steven Weinberg, one of the architects of the modern understanding of particle physics, emphasized that quantum field theory provides a framework in which the laws of physics can be expressed in a consistent and unified way. In his work, he showed how symmetry principles and field interactions can be used to construct theories that match experimental results with remarkable accuracy. But even within this powerful framework, there are important subtleties. One of them is the concept of effective field theory. The idea here is that our theories may not describe reality at all scales equally well. Instead, they are effective descriptions that apply within certain ranges of energy or length. For example, the physics that describes the behavior of atoms and molecules works extremely well at everyday scales, but it does not capture the details of subatomic particles at very high energies. In an effective field theory, we focus on the relevant degrees of freedom at a given scale. We describe what can be observed and measured, without necessarily knowing the deeper structure that may exist at smaller scales. This leads to the idea of layered reality, different levels of description, each valid within its own domain. At one level, we have chemistry, at another, atomic physics, at another, quantum field theory. Each layer builds on the one below, but also introduces new concepts and simplifications. This is not a weakness. It is a practical and powerful way of understanding a complex universe. It allows us to make accurate predictions without requiring a complete description of everything at once. And yet, It also leaves open the possibility that there are deeper layers still to be discovered. Even within quantum field theory itself, there are conceptual challenges. One of the more subtle is known as Haig's theorem. This theorem, developed in the context of quantum field theory, suggests that the interaction picture, a common mathematical approach used to describe interacting fields, may not be fully consistent in a strict sense. Without going into technical detail, the key point is that the mathematical foundations of quantum field theory are not entirely straightforward. The theory works extraordinarily well in practice. It produces predictions that match experiments to many decimal places. But when examined closely, its underlying structure raises questions. This is not unusual in physics. Many successful theories have conceptual gaps or unresolved issues. What matters is that they provide accurate descriptions within their domain while pointing toward deeper questions. And in this case, the questions are quite profound. If fields are the fundamental entities, what are these fields made of? Do they exist within space-time, or do they help define space-time itself? Are they truly continuous, or do they emerge from something more discrete? These are open areas of research, but even without complete answers, the framework of quantum field theory offers a remarkably coherent picture, a universe in which everything is built from fields, not isolated objects, but continuous structures that fill all of space. And within these structures, small excitations give rise to the particles we observe: electrons, photons, quarks, each one a specific pattern of vibration in its corresponding field. This perspective unifies many of the ideas we've encountered: the wave-like behavior of particles, the continuous nature of fields, or the role of interactions and relationships. All of these come together in a single framework, and perhaps most importantly, it continues to shift our intuition. The idea that reality is made of solid, independent things becomes less central. In its place, we find a picture that is more fluid, more interconnected, and quietly elegant. A picture in which the universe is not built from pieces, but from patterns in fields that are always present. And as we continue, this idea will expand further, because once we accept that fields are everywhere, even in empty space, we begin to ask a new kind of question. What is that space itself really like, when nothing seems to be there? If fields are the underlying fabric of reality, then particles take on a very different meaning. They're no longer the smallest pieces of matter. They're not tiny, indivisible objects sitting in space. Instead, they are events. More precisely, they are localized vibrations. Small, structured excitations in a field that exists everywhere. To picture this, it helps to return once more to something familiar. Imagine a still lake at dawn. The surface is calm, almost perfectly flat. Now imagine dropping a small pebble into the water. Ripples spread outward from the point of impact. Those ripples are not separate from the lake. They are patterns in the lake. They have a shape, a speed, and a lifetime, but they are not made of a fixed set of water molecules. The water itself mostly moves up and down, while the ripple travels across the surface. In a similar way, a particle such as an electron can be understood as a ripple in the electron field. The field itself is always present, even when it appears quiet. The particle is what happens when that field is excited in a particular way, and just like the ripple on the lake, the particle has properties. It has energy, it has momentum, it can interact with other excitations. But it is not a thing in the traditional sense, it is a process. This idea becomes even clearer when we consider how identical particles behave. Every electron in the universe has exactly the same mass, the same charge, and the same intrinsic properties. There is no variation, no individuality. This is quite different from everyday objects. No two grains of sand are perfectly identical. No two snowflakes are exactly the same. But electrons are indistinguishable in a very precise way. This makes sense if they are not individual objects. But excitations of the same underlying field. Each electron is not a separate entity with its own identity. It is the same pattern appearing in different places, a repeated vibration of a single, universal field. This begins to blur the distinction between objects and events. What we are observing is not a collection of separate things, but a series of occurrences within a continuous structure. And this opens the door to another way of thinking about reality, not just in terms of matter and energy, but in terms of information. The idea that physical systems can be described in terms of information has become increasingly important in modern physics. At a basic level, information refers to the arrangement of states, the way a system can be configured. In a quantum system, these configurations are described by the wave function, which encodes the probabilities of different outcomes. Seth Lloyd, a physicist at the Massachusetts Institute of Technology, has explored this idea in depth. He has proposed that the universe itself can be understood as a quantum computer, not a computer in the everyday sense, with circuits and screens, but a system that processes information according to the rules of quantum mechanics. In this view, every interaction, every change in a field, can be seen as a kind of computation, a transformation of information from one state to another. To give a sense of scale, Lloyd has estimated that since the beginning of the observable universe, roughly 10 to the power of 120 operations may have taken place. This is an almost unimaginable number. It reflects the vast number of interactions occurring across space and time. And it suggests that the universe is not just a passive stage where things happen. It is an active process, continuously evolving, continuously computing. This perspective connects to a broader set of ideas sometimes referred to as digital physics. In digital physics, the fundamental structure of reality is described in terms of information, computation, or discrete units. Some versions suggest that space and time themselves may be composed of tiny, discrete elements. Others focus on the informational relationships between systems. John Wheeler's idea of it from bit fits naturally into this picture. The suggestion that physical reality arises from informational processes, that what we call particles and fields may be secondary, emerging from deeper informational structures. It is important to note that these ideas are still being explored and debated. They're not part of a single established theory, but they offer a useful way of thinking about what quantum fields might represent. If a particle is a localized excitation of a field, then what defines that excitation? What gives it its identity? One possible answer is that it is defined by information, by the specific way in which the field is configured, the pattern itself, rather than any underlying substance. This shifts the focus even further away from the idea of objects. Instead of asking what something is made of, we begin to ask how it is organized, what pattern it represents, what information it carries, and how that information changes over time. This way of thinking also helps explain why quantum systems can behave in ways that seem unusual from a classical perspective. For example, in quantum mechanics, a system can exist in a superposition of states, It can be in multiple possible configurations at once, until a measurement is made. From an informational point of view, this reflects a distribution of possibilities, a set of potential outcomes encoded in the system. When an interaction occurs, one of these possibilities is realized, but the underlying structure is not a single, definite state in the classical sense. It is a richer, more flexible description. And when we combine this with the idea of fields, the picture becomes even more interesting. Fields are not just physical entities, they are carriers of information. They encode the possible ways in which excitations can occur, interact, and evolve. A particle, then, is not just a vibration. It is a specific informational pattern within a field, a pattern that can be created, transformed, and eventually dissipated. This reinforces the shift we have been exploring, from objects to events, from things to processes, from substances to patterns. Even the idea of persistence, of something existing over time, can be understood in terms of information. A stable particle is a pattern that maintains its structure through ongoing interactions. It is not static. It is continuously being sustained by the dynamics of the field. In this sense, existence is not a fixed state. It is an ongoing activity, a continuous process of becoming. And while this may sound abstract, it has very concrete consequences. It shapes how we understand interactions between particles. It influences how we describe forces, and it provides a foundation for the theories that describe the universe at its most fundamental level. So when we speak of an electron, or a photon, or any other particle, we are not referring to a tiny object moving through empty space. We're referring to a localized event, a structured excitation, a pattern of information unfolding within a field that is always present. And as we continue, this idea will expand further. Because these fields are not isolated, they interact, overlap, and influence one another, forming a complex, interconnected network. A network in which everything that happens is part of a larger, ongoing process, quietly shaping the universe moment by moment. If fields are truly the underlying fabric of reality, then an important question naturally follows. How many of these fields are there, and what do they look like when taken together? The answer, according to modern particle physics, is both structured and surprisingly rich. There is not just one field filling the universe, but many. Each type of particle corresponds to its own distinct field, and all of these fields exist everywhere, all at once. They do not take turns occupying space. They do not push each other aside. They overlap completely, coexisting at every point in the universe. To begin mapping this landscape, it helps to look at what is known as the Standard Model of Particle Physics. This framework organizes the known fundamental particles and their associated fields. At its core, the Standard Model includes two broad categories of matter particles known as fermions. These are the building blocks of matter as we experience it. The first category is the quarks. Quarks come in 6 types, often referred to as flavors: up, down, charm, strange, top, and bottom. Each of these corresponds to its own quantum field, the up quark field, the down quark field, and so on. Quarks combine to form protons and neutrons, which in turn make up atomic nuclei. For example, a proton is made of 2 up quarks and 1 down quark. But in the language of quantum field theory, this means it is a complex bound excitation involving the up quark field, the down quark field, and the gluon field that binds them together. The second category is the leptons. These include the electron, the muon, and the tau. and along with their corresponding neutrinos. Each of these particles also has its own field. The electron field is particularly familiar because excitations of this field are responsible for electricity, chemistry, and much of the structure of matter. Neutrinos, on the other hand, are much more elusive. They interact very weakly with other fields. Trillions of neutrinos pass through your body every second, mostly from the sun, without leaving any noticeable trace. Their fields are present everywhere, but their excitations are subtle and difficult to detect. In addition to matter fields, there are fields associated with forces. These are often called gauge fields. The electromagnetic field is one of the most familiar. Its excitations are photons, the particles of light. Photons carry the electromagnetic force, allowing charged particles to interact. There is also the gluon field, which mediates the strong nuclear force. This force binds quarks together inside protons and neutrons. It is incredibly strong at very short distances, but does not extend far beyond the scale of atomic nuclei. Then there are the weak force fields, associated with particles known as the W and Z bosons. These fields are responsible for processes like radioactive decay, where one type of particle transforms into another. And finally, there is the Higgs field, which plays a unique role. Unlike the other fields, the Higgs field has a non-zero value even in its lowest energy state. This means it is present in a very direct way throughout all of space. Interactions with the Higgs field give particles their mass. So when we look at the universe through this lens, as we do not see empty space dotted with particles, we see a vast continuous structure made up of many overlapping fields. At every point in space, the electron field is there, the quark fields are there, the photon field is there, the Higgs field is there, all of them, always present. And what we perceive as matter is simply where some of these fields are excited in stable, structured ways. This leads to a subtle but important shift in how we think about location. When we say that a particle is in a particular place, we are really saying that a field has a localized excitation at that place. The field itself is not confined, it is everywhere. Only the excitation is localized. It is a bit like having multiple musical instruments playing in the same room. Each instrument produces its own sound, its own pattern of vibration. But all of those sounds exist together in the same space, overlapping and interacting. The room is filled with a complex mixture of vibrations, not a collection of separate, isolated objects. In a similar way, the universe is filled with fields, each with its own properties, its own ways of interacting, and its own possible excitations. And while the standard model describes a large number of these fields, it may not be the complete picture. There are strong reasons to believe that additional fields may exist beyond those we have already identified. One example comes from the Peccei-Quinn theory, proposed by Roberto Peccei and Helen Quinn. This theory was developed to address a puzzle in the strong nuclear force, known as the strong CP problem. To resolve this issue, the theory predicts the existence of a new particle called the axion. If axions exist, they would correspond to a new field, the axion field, which would also fill all of space. Axions are particularly interesting because they are also candidates for dark matter. Dark matter is the unseen mass that appears to make up about 85% of the matter in the universe. We infer its presence from gravitational effects on galaxies and galaxy clusters, but we have not yet directly detected it. If dark matter is made of particles like axions, then there may be entire fields around us that we are not yet able to observe directly. Another possibility involves sterile neutrinos. These are hypothetical particles that would interact even more weakly than the known neutrinos. They would not participate in the standard weak interactions, making them extremely difficult to detect. But if they exist, they too would correspond to additional fields quietly present throughout the universe. These ideas suggest that the landscape of fields may be much larger than what we currently know. What we have identified so far may be only a portion of a deeper and more complex structure, and yet, even with the fields we do know, the picture is already quite remarkable. At every point in space, there is not emptiness, but a rich tapestry of overlapping fields, each one capable of being excited, interacting, and evolving. This raises an interesting question. If all of these fields are present everywhere, what does it mean for a region of space to be empty? What does it mean for nothing to be there? It turns out that even when there are no particle, no excitations, the fields themselves remain, and as we will see, even in their quietest state, they're not completely still. They exhibit subtle fluctuations, small variations that arise from the principles of quantum mechanics. So the idea of empty space begins to change. It is no longer a passive backdrop. It is an active, dynamic environment, filled with fields that are always present even when they appear calm. And this leads us to a deeper exploration of what we mean by the vacuum, not as a simple absence of matter, but as a state of fields that are never entirely at rest. If fields fill all of space, even in the absence of particles, then it becomes natural to ask a quiet but important question. What does it mean for a field to be completely at rest? What does true emptiness look like? At first glance, it might seem simple. We imagine removing all particles, all excitations, leaving behind a perfectly calm, silent background, a kind of absolute stillness. In classical physics, this idea works quite well. A field can, in principle, have a value of 0 everywhere, no motion, no energy, no activity. But when quantum mechanics enters the picture, something subtle changes. Even in its lowest possible energy state, a quantum field cannot be completely still. There's always a small amount of unavoidable activity. This is known as zero-point energy. It arises from the uncertainty principle, which tells us that certain properties cannot be precisely fixed at the same time. For a field, this means that its value and its rate of change cannot both be exactly 0. There must always be a small amount of fluctuation, a gentle, restless motion that never fully disappears. These are called vacuum fluctuations. They are tiny, temporary variations in the field, occurring even when no particles are present. You can think of them as small ripples that appear and vanish in the quiet surface of the field, not caused by any external disturbance, but arising naturally from the quantum nature of reality. These fluctuations are incredibly small. They occur on very short timescales and at very small distances, but they are not just theoretical, they have observable consequences. One of the most striking examples is the Casimir effect, first predicted by the Dutch physicist Hendrik Casimir in the 1940s. This effect involves two uncharged and parallel metal plates placed very close together in a vacuum. When the plates are separated by a tiny distance, on the order of a few nanometers, something interesting happens. They experience an attractive force, pulling them toward each other. At first, this might seem surprising. There are no charges involved, no obvious forces acting between the plates. But the explanation lies in the behavior of vacuum fluctuations. Between the plates, only certain wavelengths of fluctuation are allowed. Outside the plates, a wider range of fluctuations can occur. This creates a slight imbalance in the pressure exerted by the quantum vacuum. The result is a measurable force pushing the plates together. This effect has been confirmed experimentally with high precision. It is a clear demonstration that what we call empty space is not empty at all. It is filled with activity, a continuous subtle motion of fields that never fully comes to rest. This idea becomes even more intriguing when we consider its implications on a larger scale. Yakov Zeldovich, a Soviet physicist working in the mid-20th century, explored the connection between vacuum energy and cosmology. He realized that the energy associated with vacuum fluctuations should contribute to the overall energy density of the universe. In the context of general relativity, energy density influences the curvature of space-time. This means that the quantum vacuum could, in principle, affect the expansion of the universe. This idea is closely related to what is known as the cosmological constant. Originally introduced by Albert Einstein, the cosmological constant represents a uniform energy density filling space. In modern terms, it can be associated with vacuum energy, but here a puzzle emerges. When physicists attempt to calculate the energy of the quantum vacuum using quantum field theory, they arrive at a value that is extraordinarily large, many orders of magnitude larger than what is observed through cosmological measurements. Observations of the universe, particularly those involving distant supernova and the cosmic microwave background, suggest a much smaller value. The difference between the theoretical prediction and the observed value is enormous, often described as one of the largest discrepancies in physics. This is known as the cosmological constant problem. It remains an open question, a reminder that even our most successful theories may still be incomplete, and yet despite these uncertainties the core idea remains clear. Empty space is not a passive backdrop. It is an active, dynamic environment, filled with fields that are constantly fluctuating even in their lowest energy state. This changes how we think about the vacuum. It is no longer simply the absence of matter. It is a particular state of the fields, the state with the lowest possible energy but not zero energy. A kind of quiet baseline, always present. And these fluctuations are not isolated. They can interact with particles and with each other. They can influence physical processes in subtle ways. For example, vacuum fluctuations play a role in processes like spontaneous emission, where an excited atom releases a photon. Even if no external electromagnetic field is present, the atom can still decay, in part because of the ever-present fluctuations of the electromagnetic field. In this sense, the vacuum is not just a background. It participates in physical processes. It contributes to interactions. It helps shape the behavior of particles and fields. This leads to a deeper realization. What we perceive as interactions between particles, forces, exchanges, collisions, may ultimately be rooted in the behavior of the fields themselves. The fluctuations, the excitations, the ways in which fields influence one another, all of these are part of a continuous underlying activity. So when we think of empty space, it can be helpful to let go of the idea of nothingness. Instead, we can imagine a vast, quiet sea, not perfectly still, but gently moving, and filled with subtle ripples that appear and disappear. A sea that is always present, even when no visible waves rise above its surface, and within this sea, everything we observe, every particle, every interaction, emerges as patterns of motion. Small disturbances that carry energy interact and evolve. The vacuum then is not the absence of reality. It is one of its most fundamental expressions, a state that is never truly empty and never completely at rest. And as we continue to explore how fields interact and give rise to forces, this dynamic view of the vacuum will remain essential, because it is within this quietly active background that the deeper structure of the universe begins to reveal itself. If everything is made of fields and particles are simply excitations within those fields, and then another question naturally begins to take shape. How do these excitations influence one another? How do interactions arise? In everyday life, interactions feel straightforward. You push an object and it moves. You bring two magnets close together and they attract or repel. The sun pulls on the earth, keeping it in orbit. In classical physics, these interactions are often described as forces. But in the framework of quantum field theory, something more subtle is happening. Interactions are not simply forces acting across space. They are processes involving the exchange of excitations between fields. To make this more concrete, consider the electromagnetic interaction. When two charged particles, such as electrons, influence each other, they do so through the electromagnetic field. In quantum field theory, this interaction can be described as the exchange of photons. Photons are the excitations of the electromagnetic field. When one charged particle interacts with another, it can emit a photon, which is then absorbed by the other particle. This exchange transfers energy and momentum, producing what we perceive as a force. It's important to note that these photons are often not directly observable. They are sometimes called virtual particles. They exist briefly during the interaction, and they do not need to satisfy all the conditions that real, detectable particles must obey. But their effects are real and measurable. They are part of the underlying process that gives rise to electromagnetic forces. Richard Feynman developed a particularly elegant way of visualizing these interactions. He introduced what are now called Feynman diagrams. These are not literal pictures of what is happening in space, but rather graphical representations of mathematical expressions. Even so, they provide a helpful way to think about interactions. In a simple Feynman diagram, you might see two lines representing electrons approaching each other. At some point, one electron emits a photon, represented by a wavy line. That photon is then absorbed by the other electron. After the exchange, the electrons move away, having changed their trajectories. This simple picture captures the essence of the interaction. It shows that what we call a force is actually the result of an exchange. A transfer of energy and momentum mediated by a field. And this idea extends beyond electromagnetism. The strong nuclear force, which binds quarks together inside protons and neutrons, is mediated by gluons. Gluons are the excitations of the gluon field. They are exchanged between quarks, holding them together in a tightly bound system. The weak nuclear force, responsible for certain types of radioactive decay, is mediated by the W and Z bosons. Each of these forces corresponds to a specific field, and each interaction involves the exchange of excitations within those fields. But there is another layer to this story, one that brings in a deeper and more unifying idea, the idea of symmetry. In physics, symmetry refers to the invariance of a system under certain transformations. For example, if the laws of physics are the same regardless of where you are in space, that is a kind of symmetry. If they are the same regardless of the direction you face, that is another. Symmetry principles have proven to be incredibly powerful in shaping our understanding of physical laws, and in the context of quantum field theory, they play a central role in determining how the fields interact. One of the most important developments in this area came from the work of Chen-Ning Yang and Robert Mills in the 1950s. They developed what is now known as Yang-Mills theory, a type of gauge theory. Gauge theory is based on the idea that certain symmetries can be applied locally at each point in space and time, not just globally, but independently at every location. To maintain these local symmetries, additional fields must be introduced. These fields are what we recognize as the force-carrying fields. In other words, the existence of forces can be understood as a consequence of symmetry. If a system has a certain type of symmetry, then the interactions required to preserve that symmetry give rise to fields and forces. This is a profound idea. It suggests that forces are not separate ingredients added to the universe. They emerge naturally from the requirement that certain symmetries hold. And this leads to a geometric way of thinking about interactions. In gauge theory, the fields associated with forces can be interpreted as connections in an abstract space, a kind of internal space that describes the possible states of a system. The way these fields change from point to point can be thought of as a kind of curvature, similar in spirit to how gravity in general relativity is described as the curvature of space-time. While the details are mathematically complex, the core idea can be expressed simply. Interactions arise from the structure of the fields, from the way they are arranged and how they change across space, from the geometry of the underlying system. So instead of thinking of forces as pushes and pulls between objects, we begin to see them as features of the fields themselves, as properties of the geometry of the system. This perspective unifies many different interactions under a common framework. Electromagnetism, the strong force, and the weak force can all be described using gauge theories, each with its own symmetry group, its own fields, and its own patterns of interaction. And this brings us back to the idea of exchange. The exchange of particles is not an isolated process. It is part of a larger structure defined by symmetry and geometry. The particles that are exchanged, photons, gluons, Gabio's bosons, are manifestations of the underlying fields, and the rules governing their interactions are determined by the symmetries of those fields. In this way, interactions are not separate from the fabric of reality. They are expressions of it. They arise naturally from the properties of the fields that fill all of space, and they follow patterns that are deeply connected to symmetry and structure. There is something quietly elegant about this. The idea that the forces we observe, the interactions that shape the behavior of matter, are not arbitrary. They are rooted in the fundamental symmetries of the universe, and they're carried out through the continuous exchange of excitations within fields. So when two particles interact, what is really happening is not a simple collision or a direct push. It is a coordinated process, a subtle exchange of energy and information, a momentary connection between patterns in different fields, all taking place within a vast interconnected system. And as we continue to explore this system, we begin to see that these interactions are not just local events. They are part of a larger unified structure, one that can be mapped, studied, and understood through the language of quantum field theory. A structure in which geometry, symmetry, and exchange come together to shape the behavior of everything we observe. And in this view, the universe becomes something more than a collection of objects. It becomes a network of interactions, a continuous dynamic interplay of fields, quietly unfolding everywhere at once. As the idea of quantum fields matured, physicists began to notice something remarkable. Despite the complexity of nature, Many of the known particles and interactions could be organized into a single coherent framework. This framework is known as the Standard Model of particle physics. It is not a single equation nor a simple diagram, but a carefully constructed theory built from quantum fields, symmetry principles, and experimental evidence. At its core, the Standard Model describes a set of fundamental fields and the ways in which they interact. Each particle we have discussed corresponds to one of these fields: the electron field, the quark fields, the photon field, the gluon field, the weak force fields, and the Higgs field. All of them woven together into a consistent structure. What makes the Standard Model especially powerful is not just that it lists these fields, but that it specifies how they interact with extraordinary precision. It tells us which interactions are allowed, which are forbidden, and how likely different processes are to occur. These predictions can be tested in experiments, often with astonishing accuracy. One of the main places where these tests are carried out is at CERN, the European Organization for Nuclear Research. Located near Geneva, CERN operates some of the most advanced particle accelerators in the world. The most well-known of these is the Large Hadron Collider. This machine accelerates protons to speeds extremely close to the speed of light, and then collides them. The energies involved are immense. Each collision recreates conditions similar to those that existed a tiny fraction of a second after the beginning of the universe. By analyzing the debris from these collisions, physicists can test the predictions of the Standard Model. They can look for known particles, measure their properties, and search for signs of new physics. One of the most celebrated achievements of this effort came in 2012, when the Higgs boson was discovered. This particle is the excitation of the Higgs field, and its existence had been predicted decades earlier. Its discovery confirmed a key part of the Standard Model. It showed that the mechanism responsible for giving particles mass is indeed present in nature. Experiments at CERN and other laboratories around the world have tested the Standard Model in many different ways. So far, it has passed these tests with remarkable success. Predictions involving the magnetic moment of the electron, for example, match experimental measurements to an accuracy of more than 10 decimal places. This level of agreement is almost unparalleled in science. And yet, beneath this success, there are important subtleties. One of them involves a concept known as renormalization. When physicists first began working with quantum field theories, they encountered a problem. Calculations often produced infinite results. Quantities like the mass or charge of a particle would come out as infinitely large. Clearly, this could not be correct. Renormalization is a method developed to address this issue. It involves redefining certain quantities in a way that absorbs these infinities, allowing the theory to produce finite or meaningful predictions. Kenneth Wilson made significant contributions to our understanding of renormalization. He showed that it is not just a mathematical trick, but a reflection of how physical theories depend on scale. At different energy scales, different aspects of a system become important. Some details can be ignored, while others must be included. This leads to the idea that our theories are effective descriptions, valid within certain ranges. They capture the relevant behavior at a given scale, without necessarily describing the deepest level of reality. This perspective fits naturally with the layered view of physics. The Standard Model is extremely effective at describing phenomena up to very high energies. But it may not be the final word. There may be deeper layers, with additional fields, interactions, or structures that become important at even higher energies or smaller distances, and there are clear signs that the Standard Model is incomplete. For one thing, it does not include gravity. The gravitational interaction described by general relativity is not part of the Standard Model framework. This means that one of the 4 known fundamental forces is missing from the theory. Another limitation is that the Standard Model contains a number of parameters that must be determined experimentally. These include particle masses, coupling constants, and mixing angles. There are several dozen such parameters. The theory does not explain why these values are what they are. They must be measured and inserted into the model. This raises a natural question. Is there a deeper theory that determines these values, or are they simply fundamental constants of nature? There are also phenomena that the Standard Model does not fully explain. Dark matter is one of the most significant. Observations of galaxies and galaxy clusters indicate that there is more mass present than can be accounted for by visible matter. The Standard Model does not include a particle that can serve as a suitable dark matter candidate. Another example is neutrino mass. In its original form, the Standard Model predicted that neutrinos should be massless, but experiments have shown that neutrinos do have a small non-zero mass. This requires modifications to the theory, and then there is the matter of the cosmological constant, which we encountered earlier. The vacuum energy predicted by quantum field theory does not match the observed expansion of the universe. This suggests that our understanding of the vacuum, or of gravity, or both, is incomplete. Despite these limitations, the Standard Model remains one of the most successful scientific theories ever developed. It provides a consistent and accurate description of a vast range of phenomena. It allows us to predict the outcomes of experiments with extraordinary precision, and it has guided the discovery of new particles and interactions. But it is important to remember that it is a model, a representation of reality, not reality itself. It is a map, and like any map, it highlights certain features while leaving others out. It is incredibly detailed in some areas and less so in others. It helps us navigate the landscape of fundamental physics, but it does not capture every aspect of the terrain. This perspective keeps the door open. It allows for the possibility that there are deeper structures yet to be discovered, new fields, new symmetries, new principles that extend beyond the current framework, and as we continue to explore, both experimentally and theoretically, the Standard Model serves as a foundation, a starting point, a remarkably accurate guide to the behavior of the known fields and particles, but not the final destination, because the story of the universe, like the fields that compose it, is still unfolding. Among all the fields that fill the universe, one stands out as especially unusual. It does not simply sit quietly in the background, waiting to be excited. It plays an active role in shaping one of the most familiar properties of matter, mass. At first, mass seems straightforward. Objects have mass, and that mass determines how they respond to forces. Heavier objects are harder to accelerate. They carry more inertia. But when we look more closely at the equations of the Standard Model, something surprising appears. Many of the fundamental particles in their simplest description are naturally massless. The equations themselves do not require them to have mass, and yet in reality particles like electrons and quarks clearly do have mass. So where does it come from? The answer lies in what is known as the Higgs field. The Higgs field is a quantum field that exists everywhere in space, much like the other fields we have discussed. but unlike most fields, its lowest energy state is not zero. Even in its calmest, most stable configuration, the Higgs field has a non-zero value. This means that it is always present in a very direct way, permeating all of space. Everywhere you are, the Higgs field is there, and every particle that interacts with it feels its presence. To understand how this gives rise to mass, it helps to think in terms of interaction rather than intrinsic property. When a particle moves through the Higgs field, it interacts with it. The strength of this interaction determines how much the particle resists changes in motion. In other words, it determines the particle's mass. Some particles interact strongly with the Higgs field and acquire a large mass. Others interact only weakly and remain relatively light. And some, like the photon, do not interact with the Higgs field at all, and therefore remain massless. An analogy is sometimes used to make this idea more intuitive. Imagine moving through a crowded room. If no one notices you, you can pass through easily without resistance. But if people gather around you, slowing your movement, it becomes harder to move quickly. In this analogy, the crowd represents the Higgs field, and the resistance you feel corresponds to mass. It is not a perfect analogy, but it captures the essential idea. Mass is not simply a built-in property of a particle. It arises from interaction with a field that is always present. The existence of the Higgs field was first proposed in the 1960s by several physicists, including Peter Higgs, François Englert, and Robert Brute. They were exploring how to preserve certain symmetry principles in the Standard Model while still allowing particles to have mass. Their solution involved what is known as spontaneous symmetry breaking. The idea that the underlying laws have a certain symmetry, but the state of the system does not fully reflect that symmetry. The Higgs field takes on a specific value throughout space, breaking the symmetry in a controlled way and allowing particles to acquire mass. For many years, this was a theoretical idea. There was no direct evidence that the Higgs field existed, but the theory made a clear prediction. If the Higgs field is real, then it should have an associated particle, the Higgs boson. This particle would be an excitation of the Higgs field, just as the photon is an excitation of the electromagnetic field. In 2012, experiments at the Large Hadron Collider at CERN provided strong evidence for the existence of the Higgs boson. Say, two large research collaborations known as ATLAS and CMS independently observed a new particle with properties consistent with the predicted Higgs boson. This was a major milestone. It confirmed that the Higgs field is not just a mathematical idea, but a real part of the physical world. And yet, even with this success, deeper questions remain. One of the most important is known as the hierarchy problem. This problem arises when we consider the mass of the Higgs boson itself. In quantum field theory, the mass of a particle is influenced by interactions with other fields and fluctuations in the vacuum. When physicists calculate the expected mass of the Higgs boson, they find that it should be extremely large, driven by contributions from very high energy processes. However, the observed mass of the Higgs boson is relatively small, about 125 giga-electron-volts. This is many orders of magnitude smaller than the naive theoretical expectation. To reconcile this, the theory requires a delicate balance between different contributions, a kind of fine-tuning, where large terms nearly cancel each other out to produce a much smaller result. This situation feels somewhat unnatural. It suggests that there may be additional mechanisms or symmetries that we do not yet understand. Various ideas have been proposed to address this. One class of theories introduces new symmetries that protect the Higgs mass from large corrections. Another approach involves entirely different mechanisms for generating mass. Technicolor theories, for example, and they propose that mass arises from new types of strong interactions rather than from a fundamental scalar field like the Higgs. In these models, the Higgs boson is not a fundamental particle, but a composite state, similar in some ways to how protons and neutrons are composed of quarks. So far, experimental evidence has not confirmed these alternative models, but they remain active areas of research, and they highlight an important point. Even though the Higgs field successfully explains how particles acquire mass within the standard model, it may not be the final story. There may be deeper layers of structure that give rise to the Higgs field itself. This leads to a broader question. Why does the Higgs field exist at all? Why does it have the specific value that it does? Or why do different particles interact with it in the ways that they do? At present, these questions do not have definitive answers. They point to the limits of our current understanding, and they remind us that even the most successful parts of our theories may be part of a larger, more complete framework that we have yet to discover. Still, the Higgs field offers a remarkable example of how the properties we take for granted can emerge from deeper processes. Mass, which feels so tangible and immediate, is not simply an intrinsic feature of matter. It is a result of interaction, a consequence of how particles move through a field that fills all of space. And in this way, the Higgs field reinforces a theme that has been quietly developing. The idea that what we observe, what we experience as solid and stable, is often the result of underlying patterns and interactions, not fixed properties, but emergent ones, arising from the deeper structure of the fields that build the universe. There is a quiet idea that runs through much of modern physics, shaping the laws we write down and the patterns we observe. It is the idea of symmetry. At first, symmetry might bring to mind something visual, a shape that looks the same when reflected in a mirror, a pattern that repeats evenly, a balance between parts. But in physics, symmetry has a deeper and more precise meaning. It refers to the invariance of a system under a transformation. If you change something about the system, and the underlying laws remain the same, then the system has a symmetry. For example, imagine performing an experiment today and then repeating it tomorrow. If the laws of physics have not changed between those two moments, we say that the laws are symmetric in time. Or imagine performing the same experiment in two different locations. If the results are the same, the laws are symmetric in space. These symmetries are not just aesthetic, they are deeply connected to conservation laws. This connection was made precise by Emmy Noether, a mathematician working in the early 20th century. Noether's theorem is one of the most important results in theoretical physics. It states that for every continuous symmetry of a physical system, there is a corresponding conserved quantity. If the laws of physics are symmetric in time, then energy is conserved. If they are symmetric in space, then momentum is conserved. If they are symmetric under rotations, then angular momentum is conserved. These are not separate facts, they're linked through the structure of the theory. Symmetry is not just a feature of the laws, it is a guiding principle that determines how those laws behave. And yet, while the underlying laws may possess symmetry, the states of physical systems do not always reflect that symmetry. This brings us to the idea of spontaneous symmetry breaking. To understand this, it helps to consider a simple analogy. Imagine placing a perfectly round ball at the top of a smooth hill. The system is symmetric. There is no preferred direction. The ball could roll down in any direction, and the laws governing its motion are the same in all directions. But once the ball begins to roll, that symmetry is broken. It chooses a particular direction, even though the underlying situation did not favor one over another. The symmetry of the laws remains, but the state of the system no longer reflects that symmetry. In physics, spontaneous symmetry breaking occurs when a system settles into a state that does not share the full symmetry of the underlying laws. This idea plays a central role in many areas of physics, including the behavior of the Higgs field. The Higgs field has a symmetric set of possible states, but the universe selects one particular configuration. This choice gives rise to the masses of particles and shapes the structure of the Standard Model. But symmetry breaking is not limited to particle physics. It also appears in condensed matter systems, where it can be observed more directly. Philip Anderson, a physicist known for his work in condensed matter physics, emphasized the importance of this idea in understanding complex systems. He introduced the concept that more is different, meaning that when many components come together, new properties can emerge that are not obvious from the behavior of individual parts. For example, consider a magnet. At high temperatures, the magnetic moments of individual atoms are randomly oriented. The system is symmetric, with no preferred direction. But as the temperature decreases, the system can undergo a phase transition. The magnetic moments align in a common direction, breaking the symmetry. The material becomes magnetized. This new property, magnetism, emerges from the collective behavior of many atoms. It is not something that can be understood by looking at a single atom in isolation. This idea of emergence is closely related to symmetry breaking. When a system settles into a particular state, new structures and behaviors can appear. Properties that were not present at the level of individual components. In the context of quantum fields, this suggests that many of the features we observe may be emergent. They arise from the interactions and arrangements of fields, rather than being fundamental in themselves. Mass, for example, emerges from the interaction of particles with the Higgs field. Forces emerge from the symmetries of gauge fields. Even the distinction between particles and fields becomes less clear when viewed from this perspective. Symmetry also plays a role in determining which interactions are allowed. The requirement that certain symmetries be preserved places constraints on the form of the equations. It dictates how fields can interact, how particles can transform, and what kinds of processes can occur. This is why symmetry principles are often used as a starting point in constructing physical theories. Instead of asking directly what the laws are, physicists often ask what symmetries those laws should have. From these symmetries, the structure of the theory can be derived. There is something quietly powerful about this approach. It suggests that the behavior of the universe is not arbitrary. It follows patterns that are deeply rooted in symmetry and structure. And yet, the world we observe is not perfectly symmetric. It contains variation, complexity, and structure. This is where the interplay between symmetry and symmetry breaking becomes essential. The laws may be symmetric, but the states of the system can break that symmetry in specific ways, and from this breaking, new features emerge. This balance between symmetry and asymmetry is what gives rise to the richness of the universe. If everything were perfectly symmetric, there would be no structure, no variation, no differentiation, no complexity. But if symmetry were completely absent, there would be no guiding principles, no consistent laws. It is the combination of both that allows for a universe that is both orderly and diverse. So when we look at the world around us, we are seeing the result of this interplay. Fields that follow symmetric laws, interacting and evolving. Systems that settle into particular states, breaking those symmetries in specific ways. And from this process, patterns emerge, structures form, properties arise, all of it grounded in the deep connection between symmetry, conservation, and interaction. And as we continue, this idea of emergence will become even more important, because it suggests that the layers of reality we experience, from particles to atoms to everyday objects, may all be expressions of deeper patterns within the fields that fill the universe, patterns shaped by symmetry and brought into form through its gentle breaking. As we continue to explore the behavior of quantum fields, another idea begins to emerge, one that feels, at first, even more unusual than waves, probabilities, or fluctuations. The idea that parts of a system can become deeply connected, even when separated by vast distances. This phenomenon is known as quantum entanglement. In its simplest form, entanglement occurs when two or more particles are described by a single shared quantum state. Their properties are not independent. Instead, they are linked in such a way that measuring one immediately influences the description of the other, even if they are far apart. To understand this more clearly, imagine a pair of particles that are created together in a specific way. For example, two particles might be produced with opposite values of a property known as spin. One will be measured as up, the other as down. But before measurement, neither particle has a definite value. They exist in a superposition where both possibilities are present. What is important is that their properties are correlated. If you measure one particle and find that its spin is up, you instantly know that the other must be down. This correlation holds no matter how far apart the particles are, even if they are separated by thousands of kilometers. At first glance, this might seem like a simple coordination. Perhaps the particles carried hidden instructions from the moment they were created. But experiments have shown that this explanation does not work. In the 1960s, the physicist John Bell developed a theorem that provided a way to test whether such hidden variables could explain quantum correlations. Bell's theorem shows that if the world were governed by local hidden variables, then certain statistical inequalities must be satisfied. These are known as Bell inequalities. Experiments conducted over many years, including those by Alain Aspect in the 1980s, have repeatedly shown that these inequalities are violated. The results match the predictions of quantum mechanics, not the expectations of classical hidden variable theories. This means that the correlations observed in entangled systems cannot be explained by local properties alone. There is something more subtle at work. It is important to be careful here. Entanglement does not allow information to be transmitted faster than the speed of light. It does not enable instantaneous communication in the usual sense, but it does reveal that the quantum state of a system is not simply a collection of independent parts. It is a unified whole. The properties of one part are defined in relation to the others. This idea fits naturally within the framework of quantum fields. If particles are excitations of underlying fields, then entanglement can be understood as a property of the field itself. The field can exist in a state where different regions are correlated in a way that cannot be separated into independent pieces. In this sense, entanglement is not something added on top of the theory. It is built into the structure of the fields. It reflects the fact that the field is a continuous entity, capable of supporting complex interconnected patterns. To explore this further, physicists have developed the concept of entanglement entropy. This is a measure of how much information is shared between different parts of a system. If two regions are highly entangled, then knowing the state of one region gives you significant information about the other. If they are not entangled, then the regions can be described independently. Entanglement entropy has become an important tool in many areas of physics. It is used to study quantum phase transitions, where systems change their behavior in fundamental ways. It plays a role in understanding black holes, where the relationship between entropy, information, and geometry becomes especially important. And it has even been used in attempts to understand how space-time itself might emerge from more fundamental quantum structures. One particularly intriguing idea is that the geometry of space may be related to patterns of entanglement. In some theoretical frameworks, such as those involving holographic principles, the connectivity of space-time is linked to the entanglement between different regions of a quantum system. While these ideas are still being developed, they suggest that entanglement is not just a curious feature of quantum mechanics. It may be a fundamental aspect of how the universe is organized. At a more intuitive level, entanglement invites us to reconsider the idea of separateness. In everyday experience, objects appear distinct and independent. A chair is separate from a table. One person is separate from another. But at the quantum level, this independence is not always absolute. Systems can be connected in ways that are not visible at larger scales. Their properties can be intertwined, even when they are physically distant. This does not mean that everything is entangled with everything else in a simple way. Interactions with the environment tend to reduce entanglement, a process known as decoherence. This is one reason why classical behavior emerges at larger scales. But the underlying possibility of entanglement remains. It is a fundamental feature of quantum systems, and when we view this in the context of fields, the picture becomes even more cohesive. Fields are continuous, extending throughout space. Excitations within those fields can become correlated. Patterns can form that link different regions together. In this view, the universe is not just a collection of independent events. It is a network of relationships, a structure in which connections play a central role. And these connections are not always local or obvious. They can be subtle, encoded in the shared quantum state of a system. This perspective reinforces a theme that has been quietly developing. The idea that reality is not built from isolated pieces. It is built from interactions, relationships, and patterns. Entanglement is one of the clearest expressions of this idea. It shows that even when we try to divide the world into separate parts, there are deeper connections that remain, connections that cannot be ignored. And as we continue to explore the behavior of quantum fields, these connections will become increasingly important, because they hint at a deeper unity, a sense in which the universe, at its most fundamental level, is not fragmented, but interconnected. Not a collection of separate objects, but a continuous evolving whole. When we think about quantum fields, it's easy to imagine them as something confined to the smallest scales, something that belongs to the world of particles, atoms, and tiny interactions. But one of the most remarkable developments in modern physics is the realization that these same fields also shape the larger structures in the universe. The very distribution of galaxies, the vast web of cosmic structure, and even the overall expansion of the universe can be traced back, in part, to the behavior of quantum fields. To see how this connection arises, we can begin by considering the early universe. according to our current understanding, the universe began in a hot, dense state often referred to as the Big Bang. In its earliest moments, temperatures were extremely high, and energy densities were enormous. Under these conditions, the distinctions between different fields and particles were not as clear as they are today. The universe was filled with a kind of energetic interacting field environment. As it expanded and cooled, different fields settled into the forms we now observe. Particles acquired mass through interactions with the Higgs field. Forces separated into the distinct interactions we recognize, and structures began to form. But before galaxies, stars, or even atoms existed, something else played a crucial role, a period known as cosmic inflation. Inflation is a theory proposed in the early 1980s by Alan Guth and later developed by Andre Linde and others. It suggests that the universe underwent a brief but extremely rapid expansion very early in its history. During this period, space itself expanded exponentially. Distances between points increased by enormous factors in a very short time. To give a sense of scale, regions that were initially much smaller than a proton could have been stretched to sizes larger than entire galaxies. This rapid expansion helps explain several features of the observable universe. It accounts for the large-scale uniformity of the cosmic microwave background, the faint radiation left over from the early universe. It explains why the universe appears nearly flat on large scales, and it provides a mechanism for generating the initial irregularities that would later grow into galaxies and clusters. These irregularities originate from quantum fluctuations, the same kind of small temporary variations we discussed earlier in the context of the quantum vacuum. During inflation, these fluctuations were stretched to cosmic scales. Tiny variations in the density of energy became slightly larger or smaller regions. As the universe continued to expand and cool, these variations acted as seeds. Regions with slightly higher density attracted more matter through gravity. Over time, they grew into galaxies, clusters, and the vast cosmic web that spans the universe. This means that the large-scale structure of the cosmos, the distribution of billions of galaxies across space, can be traced back to quantum fluctuations in fields, small, random variations in the early universe, amplified by expansion and gravity. It is a striking connection. The behavior of quantum fields at incredibly small scales influencing the structure of the universe at the largest scales imaginable. In this way, quantum field theory and cosmology are deeply linked. They are not separate domains, but parts of a single, continuous story. The same fields that give rise to particles and interactions also shape the evolution of the universe as a whole. As inflationary theory developed, it also led to more speculative ideas. One of these is the concept of eternal inflation. In some versions of the theory, inflation does not occur just once. Instead, it continues in different regions of space, creating a kind of branching structure. Some regions stop inflating and form universes like the one we observe. Other regions continue to expand. This leads to the idea of a multiverse, a collection of many universes, each with potentially different properties, different values of physical constants, different configurations of fields. It is important to approach this idea with care. The multiverse is not a confirmed theory. It is a consequence of certain models, and it remains an area of active research and debate. There is currently no direct observational evidence that other universes exist, but the concept arises naturally from some of the mathematical structures used to describe inflation and quantum fields. Even without invoking multiple universes, the connection between quantum fields and cosmology is already profound. It shows that the smallest fluctuations can have enormous consequences when amplified over time. It reveals that the universe is not perfectly uniform, but contains subtle variations that give rise to structure. And it demonstrates that the same principles apply across vastly different scales. From the behavior of individual particles to the distribution of galaxies across billions of light years. This bridging of scales is one of the most elegant features of modern physics. It suggests that the universe is governed by a set of underlying principles that apply everywhere, not separate rules for the very small and the very large, but a unified framework that connects them. Of course, there are still challenges. Combining quantum field theory with general relativity remains an open problem. A complete theory of quantum gravity has not yet been achieved, and there are many details of cosmic evolution that are still being explored. But the progress that has been made already offers a remarkable picture. A universe in which quantum fields play a central role at every level, from the smallest excitations to the largest structures, from the earliest moments after the beginning of expansion to the present day. And as we reflect on this, it can be helpful to return to a simple idea, that the patterns we observe, the galaxies, the stars, the vast structures of the cosmos, are not separate from the underlying fields. They are expressions of them. Large-scale patterns emerging from small-scale fluctuations, complex structures arising from simple principles, all of it unfolding within a universe filled with fields that are always present, always interacting, quietly shaping the cosmos from the smallest scales to the largest. For all its elegance and success, quantum field theory does not provide a complete description of the universe. It is powerful, precise, and deeply insightful, but there are places where it begins to strain. Places where its assumptions no longer fit comfortably with what we observe. And one of the most important of these tensions arises when we try to bring quantum field theory together with gravity. Gravity, as described by Albert Einstein's general theory of relativity, is not a force in the usual sense. It is a description of how space-time itself curves in response to mass and energy. Objects move along paths determined by this curvature. Planets orbit stars, light bends around massive objects, and the structure of the universe evolves over time. General relativity treats space-time as a smooth, continuous entity, a geometric structure that can be curved, stretched, and shaped. Quantum field theory, on the other hand, operates within space-time. It assumes a fixed background, a stage on which fields exist and interact. This difference in perspective creates a fundamental incompatibility. In quantum field theory, space-time is given. In general relativity, space-time is dynamic. It responds to the presence of energy and matter. When we try to apply quantum principles to gravity, the mathematics becomes difficult. In fact, it becomes problematic in a very specific way. Attempts to quantize gravity using the same methods that work for other forces lead to calculations that produce infinities that cannot be easily removed. The theory becomes non-renormalizable. This means that the standard techniques used to handle infinities in quantum field theory no longer work. The result is a framework that cannot make reliable predictions at very high energies or very small distances. These difficulties become especially important in extreme situations. Near the center of black holes, for example, where gravity is incredibly strong, or in the earliest moments of the universe when densities and temperatures were extremely high. In these regimes, both quantum effects and gravitational effects are significant, and yet we do not currently have a fully consistent theory that combines them. This is the problem of quantum gravity. It is one of the central challenges in modern physics, and over the years many different approaches have been proposed to address it. One of these is loop quantum gravity, developed by researchers including Carlo Rovelli and Lee Smolin. In this approach, space-time itself is treated as a quantum object. Instead of being continuous, it is composed of discrete units, tiny loops or networks that define the structure of space at the smallest scales. In loop quantum gravity, quantities like area and volume are quantized. They come in discrete units, much like energy levels in quantum mechanics. This suggests that space-time may have a kind of granular structure at extremely small distances, on the order of the Planck length, which is about 1.6 times 10 to the minus 35 meters. At this scale, the familiar notion of smooth space may no longer apply. Instead, space may be made up of fundamental building blocks connected in a network. Another approach is known as causal dynamical triangulations, developed in part by Renate Loll and her collaborators. In this framework, space-time is constructed from simple geometric pieces, such as triangles or higher dimensional equivalents. These pieces are assembled in a way that preserves a notion of causality, thus meaning that the ordering of events in time is maintained. By studying how these structures behave when combined in large numbers, researchers aim to recover the smooth space-time described by general relativity at larger scales. In this view, space-time emerges from a more fundamental discrete structure, not unlike how a smooth surface can emerge from a collection of tiny building blocks. Both of these approaches share a common idea: that space-time itself may not be fundamental. It may be an emergent property, arising from deeper quantum structures. This is a significant shift in perspective. Just as particles were reinterpreted as excitations of fields, space-time itself may be reinterpreted as a large-scale pattern emerging from something more basic. There are also other approaches, including string theory, which proposes that fundamental entities are not point-like particles, but tiny vibrating strings. Each of these approaches has its own strengths and challenges. None has yet provided a complete, experimentally confirmed theory of quantum gravity, and this highlights an important point. Our current understanding of physics, while remarkably successful in many areas, is not complete. Quantum field theory describes 3 of the 4 known fundamental forces with great precision. General relativity describes gravity and the large-scale structure of the universe with equal elegance. But the 2 frameworks do not fully align. There is a gap between them, a place where our current theories do not yet meet. This gap is not a failure, it is an invitation, a sign that there is more to discover, more structure to uncover, more connections to understand. It reminds us that the models we use are tools. They are maps that help us navigate reality. But they are not reality itself. They capture certain aspects with great accuracy, while leaving others unresolved. And this is a natural part of scientific progress. Each new theory extends our understanding, while also revealing new questions. So when we look at quantum field theory, we can appreciate both its power and its limits. It provides a deep and coherent picture of how fields interact, how particles emerge, and how forces operate. But it does not yet tell the whole story. There are still pieces missing, still connections to be made, and perhaps, as we continue to explore, we will find that even the idea of fields, as fundamental as it seems, is itself part of a deeper layer of reality, one that we're only beginning to glimpse. As we follow the ideas of quantum fields to their limits, a quiet question begins to emerge. If fields are the foundation of everything we observe, what might lie beneath them? It is a delicate question, because quantum field theory already provides an extraordinarily successful description of nature. And yet, as we have seen, there are hints that it may not be the final layer. There may be deeper structures, more fundamental principles from which fields themselves arise. One of the most intriguing ideas in this direction is known as the holographic principle. Developed in part by Gerard 't Hooft and Leonard Susskind, this principle suggests something quite unexpected: that the information contained within a region of space may be fully described by information on its boundary, not within the volume itself, but on the surface that encloses it. At first, this sounds almost paradoxical. We're used to thinking that the contents of a space are determined by what is inside it, but the holographic principle proposes that, at a fundamental level, the description of a three-dimensional region could be encoded on a two-dimensional boundary. The idea was inspired by studies of black holes. In the 1970s, Jacob Bekenstein and Stephen Hawking showed that black holes have entropy, a measure of information content, and remarkably, this entropy is proportional not to the volume of the black hole, but to the area of its event horizon. This suggests that the information describing the black hole is stored on its surface. Extending this idea, then the holographic principle proposes that a similar relationship may hold more generally, that the physics within a region can be described by degrees of freedom on its boundary. This concept was given a more precise mathematical form in the late 1990s by Juan Maldacena. He proposed what is known as the AD-CFT correspondence. AD stands for anti-de Sitter space, a particular type of space-time geometry. CFT stands for conformal field theory, a type of quantum field theory defined on the boundary of that space. Maldacena's proposal suggests that a gravitational theory in a higher dimensional space can be equivalent to a quantum field theory without gravity in one fewer dimension. In other words, two very different descriptions can encode the same physical reality, one involving gravity and curved space-time, in the other involving quantum fields on a boundary. This duality has been studied extensively and has provided deep insights into both quantum field theory and gravity. It suggests that space-time itself may not be fundamental. It may emerge from more basic quantum relationships, patterns of information that, when viewed in a certain way, give rise to the geometry we experience. Another line of thought explores the idea of emergent gravity. Eric Verlinde has proposed that gravity may not be a fundamental force at all. Instead, it could arise as an emergent phenomenon, similar to temperature or pressure in thermodynamics. In this view, gravity emerges from the statistical behavior of microscopic degrees of freedom, from the way information is distributed and how systems tend toward equilibrium. This approach connects gravity to concepts like entropy and information. It suggests that what we perceive as gravitational attraction may be related to the tendency of systems to maximize entropy, to move toward states that are more probable. While this idea is still being explored and tested, it offers a different perspective, one in which gravity is not a basic interaction, but a large-scale effect of deeper processes. There are also approaches that focus on the structure of quantum entanglement. In recent years, researchers have begun to explore the possibility that space-time itself emerges from patterns of entanglement. One tool used in this area is the concept of tensor networks. These are mathematical structures that describe how quantum systems can be connected through entanglement. In certain models, the geometry of space can be related to the pattern of connections in a tensor network. Distances, in a sense, reflect how strongly different parts of the system are entangled. Regions that are highly entangled appear close together, while those with weaker connections appear farther apart. This suggests that space itself may be a kind of emergent property, not a fixed background, but a result of underlying quantum relationships, a structure built from connections rather than points. When we bring these ideas together, a broader picture begins to form. Quantum fields, which we have treated as fundamental, may themselves be emergent. They may arise from deeper layers of structure, perhaps involving information, entanglement, or discrete building blocks. The fields we observe could be effective descriptions, accurate and powerful at the scales we can probe, but not the most basic level of reality. This is not unusual in physics. Many concepts that once seemed fundamental have later been understood as emergent. Temperature emerges from the motion of molecules. Fluid behavior emerges from the interactions of particles. In a similar way, fields may emerge from something more primitive, something that does not look like a field at all, perhaps a network of relationships, perhaps a set of informational rules, perhaps a structure that we do not yet have the language to fully describe. It is important to approach these ideas with the sense of balance. They are grounded in serious theoretical work, but many of them remain speculative. They are not yet confirmed by direct experimental evidence. They represent directions of exploration, rather than established conclusions, and yet they are guided by the same principles that have led to progress in the past. Consistency, symmetry, mathematical elegance, and agreement with known results. They attempt to resolve the tensions we have encountered, to unify quantum field theory with gravity, to explain the origin of space-time, to understand the deeper nature of reality. So as we reflect on the journey from particles to fields, and now from fields to possible deeper structures, a pattern begins to emerge. Each step reveals a layer beneath the previous one. Each layer provides a more unified and abstract description, and each raises new questions. The universe, it seems, is not built from a single final ingredient, but from a hierarchy of structures, each one emerging from the one below, and perhaps, at the deepest level, what we'll find is not a thing at all, not a particle, not a field, not even space-time, but a set of relationships, a pattern of connections, a quiet underlying order from which everything else arises, and if that is the case, then the fields we have been exploring, the vibrations, the interactions, the structures, are part of a larger story, a story that is still unfolding, one that invites us to look a little deeper and to remain open to the possibility that reality may be even more subtle than we have imagined.